This power example is a little different from the first one that I gave you because I give you some slightly different information. So we have this car that's moving, it's going to slow down, and the question is how much power is required to slow the car down in a certain amount of time. So we know that power is our work divided by our time. Well, if I look here, I don't have the work given. I have the time given, so that's good. That's 4 seconds. So it's going to be something divided by 4 seconds. So we need to figure out exactly what that is. Now, for the first equation, or the first example of power that we did, we just used the fact that work is equal to a force times the displacement. Well, if I take a look at what I have given here, I don't have a force, I don't have a displacement. So I have no idea how I would really be able to solve that very effectively. Now, I also know the work-energy theorem, and this is important. The work-energy theorem states that the work is equal to a force times the displacement, but it's also equal to a change in kinetic energy. I can use that equation, that theorem, to figure out the amount of work that's done, because I know that change in kinetic energy is the final kinetic energy minus the initial kinetic energy. And I know the velocity, I know the mass, so I can figure this out. So if I do that, if I just plug in the values that I have here, so 1/2 times 325 kilograms, times the final, which is 14 meters per second, minus 1/2 times 325 kilograms, times 24 meters per second. Again, those velocities are squared. I just have to calculate that value. So I just have to plug that into my calculator. So if I do that, 0.5 times 325 times 14 squared minus 0.5 times 325 times 24 squared, that gives me a value of negative 61,750 joules. So I know that the work is being done to take energy away from the system because kinetic energy is going down. So then to figure out the amount of power that's done, power is just a scalar, so the negative value doesn't really matter when we're talking about the power here. So the power is going to equal this work. So I'm not going to worry about the negative, so 61,750 joules, again, because it's just a scalar, divided by the 4 seconds. And that's going to give us the rate of power. So 61,750 divided by 4 is 15,437.5 watts. That's a pretty good amount of power, but that's also a pretty big change in speed or the velocity of this car in a pretty short amount of time. So it would take a pretty good amount of power to figure that out. But again, don't worry about the negative because power is just a scalar quantity, so you don't need to worry about the positive and negative. I'm not worried if it's a positive or negative. The negative matters for the work, just to say that it's coming, that the amount of energy is coming out of the system, but it doesn't really matter for the power.